So let me spell out the schedule here. Today's Wednesday. I have office hours tomorrow. Homework 3 is due on Monday, and then the exam will be the following Friday. Okay. We have 3 warm-up questions, so let's dive into those. The first 2 are connected, and I normally trip people up on the second, so we'll see how you do. But here's the first one. Last time we were talking about thermal spectra, black body spectra, and its properties, such as the peak or the total emission, given by Wien's law and Stefan's law, and you'll need to figure out which to apply where. So in this question, we're looking at a 4,000 Kelvin star. That's the surface temperature of the star. And it's emitting a spectrum. And the spectrum peaks at what wavelength in nanometers? That's the question. Now, I'll give you just a few more seconds since many of you have been here for a while and have already answered it. I think we have about 100 people here today. This is good practice for the homework and for the exam. Guarantee to have a question like this on the exam.
When will you release all of the warm-up questions?
I normally do it after I've given you the last question related to lesson 3. And so that should be Monday's class. I hope to wrap up all the material for lesson 3 on Friday. I'll probably have one final warm-up question tied to that material, so after class on Monday. Okay,
thank you.
So will Wednesday then function as like a review class, or what are we doing?
It won't be a review class. So the homeworks are the review. The homeworks are designed to get you ready. I'll just be moving straight into lesson 4 on Monday, and I'll use Monday and Tuesday for that. If you have questions, come to office hours, but otherwise the homeworks and the warm-up questions are designed specifically to get you ready for the exam. Once you see the exam, they will look familiar. I'm not going to be giving the same questions, but be very much the same style of questions.
But lesson 4 will not be on.
Lesson 4 will not be on the exam, but we will begin the material on Monday.
Dr. Reichert?
Yeah.
In calculating the formula for the warm-up, for the wavelength peak, are we always using 0.29 centimeters?
You can use that version. That's the version that's in the textbook. Last time, and also in the ebook, I give a version that's already in nanometers. You'll see that in just 1 second. So, any other questions? And we'll take a look at the answer. Okay, let's see how you did. Showing the values looks pretty good. We have our histogram there. And I could probably add bins, but it's pretty clear you all got that. So let's take a look at the answer. So here's the version of that equation that I gave last time. Let me reveal all the dot cam. It's the same equation as 0.29 centimeters divided by the temperature in Kelvin. Here I've just changed the units to nanometers, since often light, wavelengths of visible light anyway, are measured in nanometers. And often with, for example, stars, we tend to measure them in thousands of Kelvin. So this should be easier, faster to use, fewer unit conversions. So in this case, you're just plugging in 4,000 for the temperature. So you're talking about 2,900 nanometers divided by 4, which is 725 nanometers. So good. That's Wien's law, and you all seem pretty adept at using it. So now this question, and there's a question like this on the homework as well. I'll reset the board here. Okay, you've calculated the peak wavelength, 725 nanometers. What color is the star? Oh, yep, got it. What color is the star? Is it too red to see with the human eye? Is it red? Is it blue? Or is it too blue to see with the human eye? This one's a little trickier, but it ties into a key concept we talked about last time. See, I think we had about 60 responses last time. Let's see if we can get it up to that. Okay. Show values, and let's see, it was a 1, 2, 3, 4 questions. So from 1 to 4. Show histogram, and you are tied between 1 and 2. And let's see, 1 and 2 are too red to see with the human eye and red. So I'm gonna throw you into the break rooms and you can discuss. It is one of those two. It's 1 or 2. So give me a second just while I remember how to do this. Breakout rooms. I picked a number of rooms. Let's try 40 rooms maybe. Okay, and off you go. Okay. Hello? Hey, I'm teaching right now. Do you need me? Okay, I'll be right there. Okay. Okay.
Reset the question so we can answer.
Yes, sorry. My son was locked out. I had to run down and open the door. But okay, and I just ended the break rooms. Everyone will be coming back. Go ahead, you can answer. Okay, everyone's back now. Go ahead and put your answer in. Okay, it's going to be between 1 and 2. Most of you answered 2, and that is correct. So let's see, 2 was red. Now many of you probably answered too red to see because when you did the Wien's law calculation, you got 725 nanometers. And you probably remember from last class, the human eye works between 400 and 700. So 725 is slightly out of the range of what the human eye can see. But what that means is we can't see the peak of the spectrum. But you have to remember that the thermal spectrum is quite broad. Let me pull up the figure here. In fact, we have 4,000 on here as one of the examples. The peak is just a little bit too red to see, but it's a broad distribution. And I wasn't asking you if the peak was visible. I was asking you if the star was visible. And you can see that this distribution does intersect the visible band. And since the peak is over in the infrared, that means there's going to be more red light than blue light. So the star is indeed visible and it's red. In fact, a star as cold as 1,000 Kelvin will be visible. It'd be kind of faint, but it will be red. Now, if you get down to about 300 Kelvin, which is like our body temperature or room temperature, no, you're not going to see any visible light. Okay? that should help you answer one of the trickier ones in the homework. And again, you'll probably see something like that on the exam as well. That make sense? Okay.
Professor, I have a question.
Yeah, go ahead.
So, for example, like the 300 Kelvin, so if it does not intersect the visible spectrum at all, then you just say that, like, assume that like it's, we're talking about the peak for 300 Kelvin. Would it then be too red to see, or?
Yeah, then it would be too red to see. All the light is coming out redder than red. So too red to see. That's what I mean by that.
So 1000 Kelvin? Oh, okay.
1000 Kelvin.
So for 1000 Kelvin, okay.
Yeah, you have a little bit of red light there. And, you know, and very little yellow and negligible amounts of green and blue. So super red and super faint. Get up to 4000 and you have a red distribution. Remember, this is a powers of 10 plot. So going up from here, this level to this level is about 10 times as much. So you have about 10 times as much red as blue here. And we keep going up higher, then it becomes bluer. You run through that sequence of colors we mentioned last time, from red to orange to yellow white to blue white, and then to a thermal blue. I'll come back and ask you more about that in a second. I have one more warm-up question for you today. This connects to the other type of question we were asking about. Okay, so star A is 6000 Kelvin, star B is 5000 Kelvin. Star A emits how many times more energy per unit time per unit surface area? So if you were to take 1 meter of its surface in, let's say, 1 second of time, how much more energy do you get out?
Dr. Rockhart,
Yeah,
what is the setup of the exam going to be?
so the exam, it will be in WebAssign. It will be 25 multiple choice questions. In fact, I think they're all, for the exams, they're all multiple choice, no multiple select. And about 2/3 would be conceptual, about 1/3 would be calculational, just like in the homeworks. Except with the calculational ones, most of them will be a single step. In the homeworks, they've tended to be 2 steps to give you more practice.
Okay, thank you.
Okay, go ahead and submit your answer. And let's get it up to about 60, and then we'll take a look. Maybe we'll go with the low 50s this time. So you can keep submitting, but let's take a peek. So we got one number that's crazy high. Maybe I'll cut it off at 100 here. And we have 2 primary answers, 1.2 and 2.1. And I know where both of those come from. 2.1 is the correct answer. 1.2, I think, is what you got if you didn't raise it to the power of 4. So let's throw the math up here. So this is Stefan's law. And what it's telling you is how much energy is under this curve. I'll just throw this back up here for a second. How much energy is under this curve across all frequencies. And that's the energy that's coming out every second per square meter. And energy flux is proportional to temperature to the 4th power. And the constant proportionality is something we call the Stefan-Boltzmann constant. But again, like many things in this course, you're not going to need to know that. And then the same equation is true for star B. And so you take the ratio of those two, the constants cancel out, and it's all about the ratio of the temperatures to the 4th power. So 6,000 divided by 5,000, there's the 1.2 that we saw. You got to remember to raise that to the 4th power. You'll probably need a calculator for that, and that gets you the 2.1. So over twice as much energy is coming out of the slightly hotter star. You change the temperature a little bit, and you get a lot more energy. And this is true for any thermal emitter, not just stars. You can do this with your oven. You know, double the temperature of the oven, you'll get 16 times more energy to come out. Okay. Those are the warm-up questions. Questions about any of that?
Could you put that little graphic back up on the screen that explained that last warm-up question?
This right here?
Yeah, thank
Yep, go ahead. And really, you know, when I put this here, I'm spelling it out in detail, but you should be getting to the point where you just remember energy flux is proportional to temperature to the 4th. So I'm making it 1.2 times as hot, so it's going to be 1.2 to the 4. And you actually don't have to go through all these steps and cross out the constant. You should be able to just look at the equation, and you may need a calculator to do the exponentiation, but it should be pretty quick and easy. So these make for great exam problems. Hint, hint. Okay. Now let's see. Last time I gave you a video assignment. The question is, why is there no green stars? So again, the sequence, and we saw this, and I had the incandescent bulb here last time, and as I increased the voltage going into the bulb, we saw two things. We saw Wien's law, we saw the color change, so the peak moved from the red to the blue, and we also saw, sorry, that was, I forgot what I said, but that was Wien's law, and we also saw Stefan's law, where it became brighter as I increased the voltage. Now the color sequence we saw, it started out red, orange, yellow, and then we know the next color in the rainbow is green, but we didn't see green. We saw yellow, white, then we saw white, then we saw blue, white. If I could have kept going, the light bulb would have turned blue, a particular shade of blue that we call thermal blue. But the voltage had a maximum. I couldn't go any farther. So the question is, why no green? And the same is true with stars. We look up at the stars, we see all these different colors, but we don't see green stars. And there are two reasons. There's a fundamental reason, then there's a technical reason. Anyone want to give me one of those two reasons?
The green has, like, when it peaks in the green, it has all of the colors in the visible light spectrum, so it comes out as white.
Correct. And so here we have, I showed you this plot before. It's the spectrum of the sun. The sun peaks, it says 6,000, but it's really 5,800, kind of between red and yellow. And so you get similar amounts of red, orange, yellow, but you get lesser amounts of green and blue. So the sun is not perfectly white. It still has that yellow tint. Again, it's a powers of 10. So if you're just a little bit higher, that's a lot more. It's kind of white minus some of the green and blue. But if we go to slightly higher temperature, maybe about 6,500 Kelvin, then you can see the peak is over here in the green. And since this distribution has a certain shape, but the top is kind of flat, at least over a narrow range of frequencies, and the visible band is pretty narrow. So when you're at 6,500, you have almost the same amount of red, the same amount of green, the same amount of blue. And the human eye, it has three color sensors, the red, the green, and the blue. If you have similar amounts of each, it comes out as white. The brain interprets it as white. So that's why there are no green stars. It's just, to our human eye, the way our brain receives this information at three different frequencies and combines it, we combine it to white instead of to green. Now there's a secondary question that I addressed in the video. We'll see if You remember that. When you look up at the sky at night, all the stars appear white, for the most part. There are a few that you can maybe get a tint of red or blue, but most of them, they appear white. Does that mean all the stars that we're looking at are 6,500 Kelvin? Or is something else going on?
It's because they're farther apart, right? The stars are so far that our eyes can't see the actual colors of the star.
Yeah, they're so far, which means that the starlight is quite faint by the time it gets to us. And what does that mean in terms of how does the human eye respond with a faint amount of light?
It's too dark for our cones to like distinguish the colors, so we just see it in black and white with our rods.
Exactly. So the human eye, it has cones and rods. Cones are color sensitive. That's the red, green, blue sensors. And those are on the middle of the eye. And then all surrounding that, you have the rods. And the rods are more sensitive. If you're in the lab course, you've experienced this. If you use the open filter or the high-through filter, you bring in a lot of light, you can see faint stuff. If you choose a red, a green, or a blue filter, or one of the other narrower band filters, you bring in less light. So if it's really faint, the cones fail. You don't get enough red, enough green, or enough blue to register it, but the rods can still pick it up because the rods are bringing in all the light and it's just registering as a grayscale in your brain. It's really unfortunate because the sky is full of color. Those stars are the entire range of colors that I wrote out here. We just can't see it. Now, if you put your eye up against a telescope, that boosts the amount of light that's going into your eyeball, and then you can see the colors. But just to the naked eye, maybe Betelgeuse and Rigel in the constellation Orion, you can see a tint of red and a tint of blue, and maybe a few other cases like Mars, you can see a tint of red. But otherwise, everything comes in black and white because our eye is just not sensitive enough for it. Okay, new material. So next, I want to talk about spectroscopy. Maybe I'll go to a fresh sheet for this. And I mentioned early on when we started getting into lesson 3 that astronomers work in 2 ways. Yes, we can take the light and image it onto a detector and make a picture, and we can learn a little bit about what's going on from the picture. But if we really want to get a good understanding of what's going on, we do spectroscopy. We take the light, like here's a star, and we take the light and we put that through some kind of disperser, such as a prism. Prisms aren't the best, but they're the ones that most people are familiar with, and it breaks it into its component colors. So here's the rainbow spectrum that we get from taking sunlight and dispersing it. But there are different types of spectra. Let's start with continuous, because that's what we talked about so far. So continuous. And the example that we did in class is thermal, also called black body. And if you remember from last class, the way you produce light is by shaking charge. And so thermal is just one way of shaking charge. It gives you this particular distribution of light. There are other ways. If you go on to Astro 102, we'll talk about using magnetic fields to shake charge. That gives you a different spectrum of light, and other processes as well. But thermal is our really good example of continuous. All stars have a temperature on their surface, so they emit a continuous spectrum. But there are other types of spectra as well. We have absorption line and emission line. Let me write those down. Absorption line spectra and emission line spectra. Spectra is plural for spectrum. And so we can see this here. Suppose the light on its way to us went through a cloud of gas and then continues on its way. We put it through a prism, and as long as they're all on a line, we're looking at that star, but there's a cloud of gas in the foreground blocking our view, and it's transparent gas, as we'll learn. You see the colors from the continuous spectrum down here, minus the colors at particular wavelengths or frequencies or energies. It's light, so you can describe it as frequency, wavelength, or energy. So at particular places, particular colors, you're missing the light. and it's because it was absorbed by that cloud of gas. Since these are really narrow, we call them lines, and this is an absorption line spectrum. And as we'll learn, it will have to do with how atoms behave, atoms in this cloud of gas. Now, if we then look at this cloud of gas from a different direction, we'll see light being emitted from those very same wavelengths. In this case, we're looking at the cloud, we're not looking at the background star. So the star is off to the side, we're just looking at the cloud, so it's not backlit. It's just whatever the cloud absorbed from various other directions at these discrete wavelengths, it's now re-emitting. And it'll be the same wavelengths, but you may have different intensities from one line to the next. So let's write some of this down as notes. So with the absorption line spectrum, what those lines correspond to are two things. The first is the composition of that cloud. The example that we see here is hydrogen. If this is a hydrogen cloud, this is the pattern of lines that you get, at least if the cloud is sufficiently hot. If you change the temperature of the cloud, like if it's a really cold cloud, you won't see these lines in the visible, you'll see a different set of lines in the ultraviolet. If it's a really hot cloud, you'll see a different set of lines in the infrared. And there are reasons for this that we'll learn. But the pattern of lines gives you the composition and also the temperature. You can change what pattern any element presents by changing the temperature. So this is a powerful tool. We can take incoming light from space, disperse it with a prism, look for those lines, and that's telling us things like composition, temperature. Even though it may be light years or thousands or millions of light years away, I could tell you what it's made of. I can tell you how hot it is. Then with the emission lines, again, you're getting the same pattern. It's just that light is being re-emitted in all directions. The cloud absorbs it and then it re-emits it in all directions for everyone to see. And you get the same pattern, but differing intensities for reasons we'll see. So those are the different types of spectra. What causes them? Let's tackle that next. So this will be Kirchhoff's laws. It's with one C. It has two H's and two F's, Kirchhoff's laws. And these are empirical laws. So Kirchhoff, he's a scientist from, I don't know how long ago, very long ago, and was playing around in his laboratory trying to make these different types of spectra and figured out under what conditions you get these types of spectra. So maybe I'll draw a little line here. Let's tackle continuous spectra first. And he found three ways to make a continuous spectrum. One is a luminous solid, one is a luminous liquid, and one is a hot, opaque gas. So all three states of matter, solid, luminous, solid, liquid, and gas, he was able to produce continuous spectra. Let's think of some examples. What's an example of a luminous solid? A solid that glows and produces a continuous spectrum.
Like lava?
Lava? Lava flows. I'd put that under the second category, a luminous liquid. Anything that moves, even if it's slow, it's a liquid. How about a
radioactive material?
Radioactive material, that's going to be a type of emission line spectrum. It's not going to be a continuous spectrum. There are lots of examples of things that glow that won't fall into this continuous category. For example,
A light bulb.
A light bulb, yeah. So there are two different types of light bulbs. There are incandescents and there are fluorescents. And so which one gives you a continuous spectrum?
Incandescent.
That's right. So what we looked at last time was an incandescent light bulb. It's just a little piece of metal. So again, luminous solid, metal. If you heat metal up enough, it glows. If you heat it up even more, it melts, and then you have a luminous liquid. Lava is an example of melted rock, but you've also seen melted metal as well. So you heat these things up enough and they'll glow. The fluorescent light bulbs, they're going to be an example of an emission line spectrum. They're not glowing because there's something 6,000 degrees. In an incandescent bulb, there's something 6,000 degrees in there. That's why it's glowing. But the fluorescent lights, which are much more energy efficient, they're emitting just at discrete wavelengths. And bioluminescence is similar. Fireflies, those are emission lines. You know, the firefly's butt isn't 6,000 degrees. That'd be really uncomfortable for it. So anyway, yeah, hot metal, molten lava. And for hot opaque gas, the best example is stars. Like there's gas, like in my room, in the room that you're at, the atmosphere, the air, but that's a transparent gas. We can see through it. The opposite of transparent is opaque. And we'll see these different conditions. It depends on whether you're talking about a transparent gas or an opaque gas. You can have a gas that's opaque. If the gas is dense enough and made of the right stuff, you can't see through it. And a star is a good example. And you heat it up and it will glow with a continuous spectrum. Okay, let's take the emission line case next. So for this, what Kirchhoff found is that you need a sufficiently hot or heated transparent gas. So if it's an opaque gas, it will give you a continuous spectrum. But if it's a transparent gas, it can also emit light if it's been sufficiently heated. And sufficiently, it depends on the nature of the atoms in that gas, as we'll see. But you can see here, we have a cloud of gas. It's being heated by this star. Some of the light is being absorbed, in particular at these wavelengths here, and then it's being re-emitted. It may take some time, but eventually there are atoms in there that have grabbed onto that energy. They've entered an excited state, as we'll learn. They'll de-excite, emitting that line radiation in all directions. So if we look at it from any other direction, we'll see that emission line spectrum. But the key thing is it's a transparent gas. When those atoms de-excite and emit those wavelengths, those specific wavelengths, if the gas is transparent, that light just goes all the way out. That's what transparent gas means. Nothing's going to stop it. But if you make the gas more and more opaque, that light has a harder time getting out. It starts to bounce around and run into things, and that changes it, and it thermalizes it. So the atoms may be emitting a spectrum like this, but if the light then has to travel through an opaque gas, this is what you get coming out. So as you go from transparent to opaque, the light thermalizes. Sorry. If you go from transparent to opaque, the light thermalizes, and then you're in this case here. But if it's transparent, you get the emission line spectrum. And then the last case was the absorption line spectrum. I don't feel I made good use of my space on the paper, so this is kind of 1, 2, and 3, Kirchhoff's first, second, and third laws. Absorption line, you get that if you have a backlit, sufficiently cool, transparent gas. Again, that's what we see up here with this cloud of gas, and it can be a cloud in space, or it can be gas in Earth's atmosphere. The light's traveled all the way across space, and our atmosphere is doing some of the absorbing. It could be the atmosphere of the emitting object. But anyway, if it's transparent, that's required, because if it were opaque, you wouldn't be able to see through it. You'd be looking at it instead. But if it's backlit and it's sufficiently cool, then you get the continuous spectrum minus those lines. Okay. Now, I should say Kirchhoff's laws are empirical laws. We talked about empirical law, physical law, universal law. This is empirical. He didn't explain why this is the case. He just did experiments in his lab and figured out these are the conditions. But we'll be able to explain it all once we understand atomic structure. But even before we get into atomic structure, this is a useful tool. As I said, By looking at these lines, whether it's absorption or emission, we're learning compositions and temperatures. In our labs here on Earth, we can take hydrogen, helium, all the different elements, and make it produce a line spectrum. You heat it up, it produces emission lines. Then when we look out in space, if we see that same pattern, we can identify what we're looking at. We can measure the compositions of things. So let's give that a try. We'll do that here. We'll see if you can identify the composition of gases from the other side of my office. If you can do that, then the same principle applies. You can do it out in outer space. So let's see, let me turn off this light here, make it a little bit darker in the room. And I have different tubes of pure gas. Put one in here. It says, do not put fingers in sockets when turned on. That's a good thing for me to note. And actually, before we look at that, let me give you a comparison chart. That's right here. So maybe do a screen capture of that slide. And I'm going to show you a couple different elements, and we'll break it up using the grading into a spectrum, and you tell me what element we're looking at. Okay, you have that. So here's the first one, and even before I put the grading up, you can probably identify the element just from the composite, the overall color. But in case you can't, I'll put the grading in the field of view here, and you should see the spectrum on either side, actually, on the left and the right. So look at that spectrum and compare it to the slide I just gave you and tell me, what is that?
Is it neon?
Yep, that's neon. This is the easy one. Lots and lots of reddish lines, maybe a couple yellow ones. So again, if we see this signature out there in the universe, it's neon. Okay, here's another one. I have 4 of the 5 in that slide. Maybe it's a little harder to guess this one based on its composite color, but I'll put this up here. It's a little hard because one second, let me turn the light off. There we go. So again, you have a spectrum on the left and on the right. Can you identify it based on the lines you see? From what I can tell, this dot cam is not super sensitive in the blue. I think it's missing some of the bluer or more violet lines, but based on what you see, what do you think it is?
Hydrogen?
Hydrogen?
Yep, the most abundant thing in the universe in that tube there. In this case, it's heated up sufficiently to produce, as I said, hydrogen, if it's cool enough, it will actually produce lines in the ultraviolet. If it's hot enough in the infrared, here the voltage is such that we're getting the ones in the visible part of the spectrum. Ooh, it's hot. Ouch, 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 ouch. Okay, here's another one. I'll just focus on the spectrum on the left there.
That's sodium?
Helium.
Helium. That's helium. And
Oh yeah, I was looking at the wrong spectrum.
okay, and that's the second most abundant thing in the universe. Now, helium is a noble gas. It doesn't interact with anything. So even though it's here on Earth, we didn't realize it. And we first found it in the sun, and hence the name, helium, helios. It means the sun. But it turns out it's the second most abundant thing in the universe. And I got one more. It's a little faint. The dot cam doesn't have a great blue-violet response, but what do you think that is?
Mercury?
Mercury?
That's mercury. Let's turn it off. Turn this light back on over here. Yep, that's mercury. So, you know, I'm careful with that tube. I don't want to break that tube because you don't want mercury vapor floating around. Mercury has that double, let's see it, yeah, double yellow line, but also some of these others. Sodium, the one I don't have, but it's worth mentioning, a lot of the street lights. You go out at night, there are two types of street lights, the white ones and the yellow ones. And the white ones, they're white because they're emitting all sorts of different lines, red lines, green lines, blue lines, and so they all come together and look white to us. But astronomers prefer that you use the yellow lights, because then you're really only screwing up these two wavelengths. We could put a filter over our telescopes that block just this narrow part, yellow part of the spectrum, and then the sky is dark again for us. But if you have the white street lights, then you're messing up the entire spectrum, you know, with lines all over the place. So if there's new construction, we always encourage them to use the yellow lights. Okay. So again, this is really practical even if you don't understand it, but we can try to understand it. So to do that, we're going to talk about atomic structure. Okay, that's the next topic. Here's just one more slide that's probably worth looking at. Those are all really simple examples. When we look out in space, it's really complicated. There are no clouds out there of pure hydrogen, pure helium, pure neon. It's always a mix of stuff. And so we get them all jumbled on top of each other. So you can see here, here's a real astrophysical spectrum. Here it is as an intensity plot, so lots of hydrogen, as you might expect, because there's a lot of hydrogen out there in the universe. But all these little bumps and wiggles are actual lines. And we have a certain type of astronomer called a spectroscopist who's really good at this and can take data like this and say, oh, your cloud is made of this much of all these different things, and also tell you the temperature from the various patterns, because they only, all these different patterns for all these elements only manifest themselves this way at the common temperature of this cloud. Okay. But to understand it, we have to talk about atomic structure. So let's start this and see how far we can get. Well, atoms, you know, some of this you've known forever, but some of it will be presented a little bit different. But atoms, we know that you have a nucleus with protons and neutrons in here. So you have a, I'll just write it down. You have a nucleus, protons and neutrons, and the protons have a positive charge. So the nucleus has some kind of positive charge. As we learned last time, like charges repel from the electromagnetic force. So the nucleus wants to fly apart, but the strong nuclear force is even stronger and holds those protons together in the nucleus, even though they don't like being close to each other. Then in the outskirts, you have electrons, and they have a negative charge. If you have the same number of positives as negatives, then you have a neutral atom. Now, the type of element you're looking at depends on the number of protons. So in the nucleus, you can vary the protons and you can vary the neutrons. If you have one proton, it's hydrogen. If it's two protons, it's helium, etc. 3 is lithium, and so forth. You change the number of protons, you're changing the element. But for a fixed number of protons, you can also change the number of neutrons. With hydrogen, it's typically 0 neutrons. So hydrogen is just a proton by itself, but you can also have a proton-neutron combination. We call it deuterium. You see it in heavy water. You know, H2O has 2 hydrogens. One of them could have a neutron stuck to it, then it's heavy water. Helium, typically you have 2 neutrons, but you can also have a case with just 1. We call that helium-3, and that's vital for nuclear reaction. So is deuterium. So you change the number of neutrons, it's a different isotope. The change the number of protons, it's a different element. And just to put it into context, again, this is kind of like when we started talking about the solar system. We're about to look at a lot of figures like this, and they're misleading in terms of the scale. Like all the figures we looked at, sun, earth, moon, nothing was drawn to scale, because if they did it to scale, you wouldn't see anything, because the solar system is mostly empty space. Atoms are even more so empty space. You may remember when we did the scale model of the solar system, I used this as the sun. Oh, dot cam. That is the sun, and not the bead, but the little hole in the bead as the earth. And to be at scale, this bead had to be 38 feet away. If we were to do the same thing with an atom, let's take a simple hydrogen atom, say this is the proton and this is the one electron. You'd have to put it not 38 feet away, but I calculated it before class, 4 miles away. So atoms are even more empty space. The universe at all scales, the solar system scales, the universe scales, all the way down to atomic scales. It's mostly empty space, which is kind of interesting. But the point is, we're going to look at a lot of diagrams, and you just have to keep in mind that the scale is way off, just so you have something to look at. Okay, that said, let's figure out how these atoms really work. And to do that, we're going to introduce the Bohr model. And this is something you've seen as well in high school and before, but maybe I'll present it in a slightly different way. So Bohr says, okay, the electromagnetic force, the force is proportional to 1 over the distance squared, just like gravity. So you may think that atoms would behave as little mini solar systems. If the force law is the same, maybe the electrons just orbit the nuclei, just like a planet orbits the sun. But Bohr said that's not the case. You have 2 special conditions. First of all, the orbits are quantized. And I'm not going to write orbit, I'm going to say orbital, because we'll learn it's actually something a little bit different from an orbit. So quantized orbitals, meaning you can only orbit at certain distances. With planets, we can orbit at any distance from the sun. Planets, spacecraft, we can put them in orbit at any distance from the central body. But he's saying electrons can only orbit at quantized, at specific distances. So that's kind of strange. So that's the first thing that's strange about Bohr's model. The second thing is he says that you have stable orbitals. That the electrons will orbit where they orbit stably and won't fall apart. And you think about solar systems, and at first this may seem like, okay, yeah, solar systems are stable, they don't fall apart. But solar systems are really far away from each other. Stars are really far away. Atoms are right up against each other. You're made of atoms. They're touching one another. They're bumping into each other. If another star passed through our solar system, what do you think would happen to all the planets? It's scattered all over the place. The 2 gravitational centers of the 2 stars, the planets wouldn't know what to do. They'd either be thrown off into deep space or into the stars. So if you had solar systems in close proximity, they would not be stable structures. Atoms are in close proximity, yet they are stable structures. So insisting that they're stable is kind of strange. They have to be, or else we'd just fall apart into a pile of nuclei and electrons. But something's going on that keeps us stable. So what is it? And this is the part of Bohr's model they probably did not explain to you. And the answer is the electrons, they're not traveling like planets travel around the sun. They're traveling as waves. And we've just spent a lot of time talking about waves. Here's Young's double slit experiment. You can do it with electrons. You can throw electrons against this screen one at a time. And if they were particles, you would end up with those 2 bars of electron detection. But what you end up with is the interference pattern, just like light. That means electrons, even though when we detect them as particles, means they're traveling as a wave. The electron wave went through both slits, interfered with itself, gave the interference pattern. So if electrons are traveling around the nucleus as a wave, behaves a little different than if it was traveling as a particle. And I may go just a couple minutes over today, so bear with me. But let me draw what that's like, and then I'll write down the condition. So let's say an electron is orbiting a certain radius from the nucleus there. And the case I'll draw will be 3 wavelengths. I always do a bad job with this, so I'm going to look at my notes There's 1. There's 2. There's 3. So it wasn't super symmetric, but you get the idea. And then the next time it just keeps going on top of itself. So this is an example of constructive interference. This is a wave that when it comes back around, it's in phase with itself. So it adds together. So it's more likely, it's constructively interfering, it's reinforcing itself, it's going to be there. But if I deal with a slightly larger circle, maybe this one is of a size that I get not an integer number, but a half. There's 2, there's 3, and a half. So next time it comes around, it's always opposite. So when it interferes with itself, it will interfere destructively. It's out of phase, it cancels out, and so there's nothing there. So at this distance, if the electron is a wave, at this distance, it can't exist. It cannot be at that distance because it cancels itself out. There's nothing left. There's no probability of it being there. It can be at this distance, it can be at greater distances. So let's write down the condition for that. So the condition, we have a circle, and that circle has a circumference of 2 pi times the radius. And if you can fit an integer number of waves going around, then it constructively reinforces itself. So it'd be some integer, n, equal to 1, 2, 3, etc., times the electron wavelength. I don't even need to give an expression for electron wavelength. The point is, you'll have constructive interference. You can have the electron existing when the radius is proportional to that integer, n. That's the condition. So for n of 1, 2, 3, what we call this, when n is 1, we call that the ground state. It's the lowest energy configuration. That's as close to the nucleus as the electron can be. N of 2, it means you're going to be orbiting twice as far out. That's also constructive interference. We call that the first excited state. N of 3 is the second excited state. It's a little confusing that the n's don't match with the excited state number. So I'll try to use the names typically. I'll refer to it as the ground state, the first excited state, the second excited state. But that's what you're looking at here. Here's an electron in its ground state. Here's the first excited state, twice as far out. The next one's 3 times as far out. So the point is a couple things. First of all, the orbits are quantized. There are only certain distances where if the electron travels as a wave, which we can confirm with the Young's double slit experiment, it only reinforces itself at certain wavelengths. And so that's why it's not like a solar system. You have quantized orbits, and we call those orbitals, because it's a wave and not a particle moving around in a circle. And stable. The electron can only exist at this distance, and this distance, and that distance. And each of these take different amounts of energy. If something jostles the atom and jostles the electron, tries to give it a little bit more energy, such that it would want to orbit halfway between, well, it can't. The wave can't exist partway between. It can exist here, and it can exist there. So you can jostle these things all you want. If you don't give it enough energy to hop from one level to the other, it doesn't accept it, and hence it's stable. So I'll just leave you with this last figure right here, because this is what's really going on. We'll go back and we'll draw it like this, like a planet going around a star, but that's not what's really going on. You have to keep in the back of your mind that it's a wave. It's a probability. The electron isn't moving around in an orbit. It's everywhere. And there are more advanced courses that you can take if you go into physics where you learn how to compute these probability distributions. And like here, take the first excited state. The most likely position is Bohr's, twice Bohr's radius. But in reality, it can be a little farther, a little bit closer. With some small probability, it can be really closer. The blue dots are mapping out where the electron, where the wave has high probability of being. And until we look, the electron is in all of these positions, just like a wave would be. When we look, then it magically is a particle again at one of these positions. And again, no one understands that aspect of physics. And here's the first excited state. It's a little messier, but the average is the Bohr orbital. But in reality, it's a fuzzy cloud of probability until we try to detect it. Okay, I think that's enough for today. And we'll pick up here and finish atomic structure next time and tie it back to the different types of spectra. I'll stick around for questions.
Can I see the doc cam again?
Yes.
Thank you.
What does quantized mean?
Quantized just means it's at a set of values. It can't be at any value. It can't be at any distance. It can be at this one, or that one kind of thing.
All right, thank you.
Like the integers are quantized, but the real numbers are continuous.
Thank you, Dr. Reichart.
My pleasure.
How would you define n again?
It's an integer, just 1, 2, 3. It can keep going all the way up to infinity technically. But what it means is it's the number of wavelengths that you're wrapping around that circle. N of 1 means you fit 1 wavelength around, N of 2, 2 wavelengths around.
Thank you.
So do we know that these orbitals are they elliptical or are they circles? Do we know?
They can be strangely shaped.
And I mean, that's why we can still have random electrons very, very close to like the proton or like wave. Okay, that makes sense.
Yeah, so like in this case here, even here we are in the first excited state. There's some probability the electron can get really close or is really close. When it's a wave, it's at all of these places with these different probabilities, and it can also be far away.
Okay, that makes sense. Thank you.
You may remember high school chemistry where you have like S and P and all the different, they can have strange shapes once you start filling in more electrons.
And so wait, were there only two sort of law or tenets of Bohr's models? Like the first one was the quantized orbitals and the second one was the stable orbitals?
Yep.
Is the third one?
Yeah, so they behave like solar systems, except for these two things.
Okay.
And they're both weird until you realize, oh, it's traveling as a wave. And then you'd have to have these properties.
Okay, that makes sense. Thank you.
So you're saying, excuse me. So you're saying that because it's traveling as like a wave, you have that kind of that weird kind of diagram that you kind of drew around it at the start?
Yeah. I can put that back up. So this is a little coarse or crude. The mathematics of this is a little bit more complicated, but I just start drawing how many wavelengths can I squeeze. There's 1, there's 2, there's 3. If it's an integer number of wavelengths, it comes back in phase with whatever it was. I can do the same thing with 4 or 5 or 2 or 1. But if it comes back out of phase, like here, it came back going the other direction. This one's going this way and it started going that way. The next time it'd be opposite. And so altogether, this averages out to nothing.
So when you
average with the lows.
Go ahead.
The highs average with the lows, giving you a net zero everywhere. And what these waves really are waves of probability. If it all cancels out, it means that there's no probability of it being there.
Okay. So, but like when you say like different waves and whatnot, you mean that as in like said electron, it's like probability kind of course changes like throughout certain amount of time, correct?
Yeah. So I don't know. It's kind of like when I had the spring. I didn't send a single wave. I sent a bunch of them until I had a standing pattern, like a consistent pattern where up, down, up, down, up, down. And
So it's like oscillating kind of?
yeah. And so you can think of this as a standing wave, like a certain wave pattern in the spring. And so the ups cancel with the downs in this kind of case, giving you the null points. But with something like here, it can reinforce itself. So that's a radius where you have a probable location. This is a radius where it's improbable because all the waves are canceling themselves out. You go a little bit bigger, then it's probable again.
Okay, I understand now. Okay.
Yeah, I think you also just cleared something up for me as well. So I think it's not like I'm trying to I was trying to understand why it is that it has to be constructive with itself. But so basically, like the wave would like run out of energy, and like when you described yourself using the spring, it's like you had to keep putting energy into it, like a lot more energy when it was destructive with itself. But once you found like a stable sort of loop, that could make it requires less energy, and it sort of just continues itself. Is that sort of the right idea?
In this case here, it'd be like me shaking. The spring's not a perfect analogy, but me shaking it in such a way that the shakes cancel themselves out everywhere. And
oh, okay,
I'm
yeah.
shaking it, and so there's what this corresponds to is there's no probability that the electron can be at this to have that energy. It can't have that energy.
That makes sense. It has, traveling as a wave. Okay.
Yes. And the
Wait,
greater
does
energy
the wave
you have,
represent?
the farther out it can be.
Is the wave representing like energy or the electron orbits?
So yeah, it's really representing energy. What I'm drawing here is a little bit of a cheat. I'm transitioning you from thinking of it as an orbit to thinking of it as a wave. The mathematics of it's a lot more complicated than what I've drawn here. But you understand the concept of a wave, and you understand constructive and destructive interference. So if I have a wave going around a loop, it all depends on the circumference of that loop compared to the wavelength. In this case, the wave would constantly be canceling itself out. Here, it would be constantly reinforcing itself.
So why does like this, I don't know if it's an analogy or like, why does this comparison with the wave to the atom exist? Is it just a different way of thinking about it? Or is it like mathematically how the atom acts?
It's mathematically how it acts. Again, by shooting protons, shooting electrons, but protons too, and shooting any particle travels as a wave, it turns out. But electrons in this case, if we shoot them at the Young's double slit experiment, we see the interference pattern confirming that they travel as waves, which means that they are actually everywhere simultaneously. But they're in these different locations with different probabilities. And we have this kind of electrostatic potential where, emanating from the nucleus. So that kind of shapes and confines where the wave can be.
Okay. I think I understand.
It's difficult to, the proper way to do it is something called Schrodinger's equation, which describes how the wave behaves, but that's quantum mechanics. And even then, none of it's intuitive. As I've been talking about, quantum mechanics isn't intuitive. You just accept these things like Schrodinger's equation, and you can calculate what the orbitals look like in this plot here.
Okay.
Yeah. It's a wave, but it's the probability that's represented by a wave.
So do you know that the probability is, I guess, well, true when you observe it because it turns into a particle?
That's right. Yeah. So again, with the Young's double slit experiment, once it strikes that boundary, it has to turn into a particle. It's detected at a single location. But we know it traveled there as a wave because of the interference pattern, and it picks its location probabilistically based on whatever that interference pattern looked like. You know, you have this interference pattern, you can think of it as a probability pattern. It's more likely to be in the bright spots, less likely in the dark spots. And so you can calculate this, and you can also calculate it for things like waves going around a central charge, and you end up with patterns like this in this particular diagram.
Thank you. Interesting
Sure.
stuff.
Yeah, thank you so much. I never really quite understood the whole electron cloud description for stuff until now, and it makes a lot more sense, and it's very, very fascinating, I must say. So thank you so much.
Good. It should make more sense. It should never make total sense.
Exactly. That's sort of what I've gathered from this course, and it's a fun mindset to be in. So I appreciate it. Thank you.
Sure.
Enjoy your evening.
You too. Anything
Thank you.
else? You're welcome.